Hello everyone, welcome to chapter 2. We are starting our derivative chapter. So let's first talk about what is a derivative. So derivatives, the easiest way to explain it is basically like what is the slope of the graph of whatever function, f of x, at any point in time, whatever we want x to be. So when I talk about this slope, really I'm referring to the slope of a tangent line. And if you remember what a tangent line is, it's just the line that'll only touch the curve at one point. So like on this line right here, I know I don't draw very well, but here we go. It's supposed to only touch at that one point right there. So the tangent line and the curve, it's like just touching like that. And so once we know the equation of the f of x, equation whatever the problem is, then we can figure out the slope of that tangent line at any point on that graph, no matter what x is, which is kind of cool because as you can see, the slope is going to change depending on where you are for x. Like I could draw another tangent line right here, and then its x value would be like right here. And so the slope at that particular point changes now because the tangent line changes. So because we're really looking at the derivatives kind of like a slope, we just need to know the slope formula. So think back to your Algebra 1 days. Slope was y2 minus y1 over x2 minus x1. So like out of 2 points that you were given, you could find the slope between those 2 points. So we're going to do something pretty similar to that. So let's say I'm trying to find the slope of the tangent line at this point right here. We'll call that point, I don't know, just x. So if we want to figure out the slope there, in order to find that tangent line, it's only supposed to touch once. But if I want a second point to use to find that slope, then I can draw my tangent line just a little bit higher so that I can get a second point like right here where that blue dot is. So we'll call that distance between x, so the x value here. We'll call that x value x plus h, so like wherever x was, and then I'll add something, and we'll call that distance h. So really, my first point is the point that I want. So I'll call it x comma y, but do you remember like another name for y is just f of x? So keep that in mind. So then my second point would be x plus h as the x value. And the y value would be, you know, whatever I would get from plugging in x plus h. So really we would call that f of x plus h. So now if we use the slope formula, our equation or slope formula would look like this now. With my second point as the x plus h, f of x plus h, the y2 would be f of x plus h minus the y value of my first point, which was f of x, or y, divided by x plus h, because that was my x2. x1 was just x. Okay, so this might start looking familiar to you because of that top part, f of x plus h minus f of x. I can simplify the bottom because x plus h minus x is just h. So this basically looks like that difference quotient that you guys were doing. And this is where it comes from. So we're going to be using that difference quotient to calculate the slope. However, because I'm looking for that slope of the tangent line, I actually want this line and that h value to be even smaller, because if I can get this tangent line to be closer to my x value that I originally wanted, then this slope would be a lot more accurate. So if I move this line a little bit, well, not that much, just like this a little, oh gosh. So get it close to that point, but then I moved it down a little bit. So now that x plus h point is actually closer to where I actually want it now, and that's over here. And as I can get that x plus h point to be even closer to my original point, then that will make my slope even more accurate. So I'm going to use limits. If I can find the limit as h approaches 0, so that distance between x and x plus h, if h could be as close to 0 as possible, and then I use that on the difference quotient, then that'll get me the most accurate possible slope of the curve at the given point x. So this is the definition of a derivative, how to find it, its formula, whatever you want to call it. So let's do a real basic example together. Let's say we're trying to find the derivative for f of x equals 3x minus 2 when x equals 2. So first, visually, let's take a look at this. 3x minus 2 is just the equation of a line. If we have an equation of a line, the slope is the same throughout this line. The slope of this line should be 3. So that means when I look at x equals 2, I should be getting a slope of 3. So we're going to use our definition of the derivative to find the limit as h approaches 0. So f of x plus h minus f of x divided by h will give us, so here when I'm looking for f of x plus h, I'm substituting in x plus h for x of my f of x equation. So instead of 3x minus 2, it'll be 3 times x plus h minus 2. So that's my f of x plus h. And then I'm going to subtract f of x. Actually, let me just keep things in brackets so I remember. So I don't know why I have so many parentheses, just go with it. So here in my first bracket, this is my f of x plus h. My second bracket, this is f of x, and then divided by h. So the most common mistake people do is just like plugging in things weird, or not distributing their negative for the minus f of x part. So just keep that in mind, be real careful. As you do these problems, there's always things on top that should cancel out. So if you're not getting that, you might have done something wrong. So I've gone ahead and distributed out the 3 to the x plus h, and then I have that minus 2, and then I distributed the negative to get minus 3x plus 2. So here you should be able to see that you have a 3x here, and then a minus 3x, so that's kind of nice, and then a negative 2 here, and a positive 2 here. So now things go away. Alright, so continuing on, let's write out what I have left now. So on top, I've got that 3h, everything else got canceled out, divided by h. And so if you remember our limit, we're not allowed to plug in h equals 0, because from the very beginning, we would have ended up dividing by 0 at the bottom. And so, but now that we've like canceled things out, we can even cancel out an h here, so that we end up with the limit as h approaches 0 of just 3, because then h will cancel out from the top and the bottom. And so now, if we plug in h equals 0, there's nowhere to plug it in, so our final answer is just going to be 3. So what we found is the derivative of 3x minus 2. The derivative is just 3, which tells us that the slope at any x value of f of x equals 3x minus 2 is 3. Originally, we were looking for what is the slope at x equals 2 specifically. So now, in order to find that, really all you need to do is plug in x equals 2 into our derivative, but since 3 has no x's in it, there's really nothing to plug in. So this just tells us that it's going to be a slope of 3, no matter what x value it is, even at x equals 2. Okay, so now let's do a more complicated example. Instead of a line, we are looking at the function x squared plus 1. So if you think back to all your graphs, x squared plus 1 would be a parabola that faces upwards, and we're looking for the slope of this graph at the point 0, 1, which tells us that we're looking at an x value of 0, because 0, 1 has an x value of 0. So I'm going to use the definition of the derivative to plug in x plus h into f of x, which will give me x plus h squared plus 1 instead of the x squared plus 1. And I'm going to subtract f of x from that, where f of x is just x squared plus 1. And then we're going to divide all that by h. Okay, So here, I want to make sure that I square x plus h first, because you know when we do PEMDAS, we do exponents first. If I square that, because I have stuff inside the parentheses that are being added, I have to FOIL this out. So really I'm doing x plus h times x plus h. So that'll get me x squared plus 2xh plus h squared plus 1. And then I'm going to distribute that negative to get minus x squared minus 1. Okay, so from here, we were saying before, stuff should cancel. So I see an x squared and a minus x squared, and then a plus 1 and a minus 1. Nice, stuff canceled out like it was supposed to. And then let's continue then, simplifying this down. So we're left with 2xh plus h squared on top divided by h. And again, we need to somehow cancel out with that h on the bottom so that we can actually plug in h equals 0, because we still currently can't. I can factor out an h on top though. So this will just give me h times 2x plus h on top, which now can cancel out with the h that's on the bottom. And that leaves us with just 2x plus h. Now, because I'm not going to end up dividing by 0 or anything, I can just plug in h equals 0 to get 2x plus 0, which is just 2x. So the derivative is 2x. Originally, we were asked to find the slope at the point 0, 1. So if my derivative is 2x, plugging in x equals 0 will give me the slope at the point x equals 0. So when I plug in 0, 2 times 0 is 0 from the plugging into the 2x. So the slope of our function f of x equals x squared plus 1 at the point x equals 0 is 0. Visually, if you think about this, f of x equals x squared plus 1 is a parabola that faces upwards with its vertex right on 0, 1, which is what they were asking us about. So if you think about that tangent line at that point of the parabola, you would get a line that looked like this. So a tangent line where it only touched the vertex would be a horizontal line here, which has a slope of 0. So that's visually what we've done. Okay, so let's keep going with a slightly more complicated example. So this time we're just trying to find the derivative of f of x equals 4x squared minus 5x. So we're going to use that definition of the derivative to find the limit as h approaches 0. So I've plugged in x plus h into the 4x squared minus 5 times x plus h instead of x, and then I'm subtracting 4x squared minus 5x from that. So simplifying this out, I'm going to square the x plus h squared. So this will give me, when I FOIL everything out, x squared plus 2xh plus h squared minus 5x minus 5h is what I get from distributing that up. And then I'm going to distribute my negative for the 4x squared now plus 5x. I'll divide by h. And then let me distribute out that 4. So 4x squared plus 8xh plus 4h squared, and then the rest of it. Okay, so again, we want to make sure that I'm able to cancel out some things that are on top. So I see I have a 4x squared and a negative 4x squared, a negative 5x and a positive 5x. So think of it as like everything in the f of x area should get canceled out. Okay, so from here, I think that's everything. Let me just simplify the top a little bit, rewrite that so it looks nicer. Okay, so again, remember we always also want to cancel out whatever's on the bottom so that we don't end up dividing by 0 when we plug in h equals 0. So that means I'm going to factor out an h on top so that I can cancel out that h with the stuff on the bottom. And that'll leave me with 8x plus 4h minus 5 on top. which means at this point, since I no longer have an h on the bottom, I can just plug in 0 for h now. So 8x plus 4 times 0, because I'm plugging in 0 for h, leaves me with 8x minus 5. So 8x minus 5 is the derivative of 4x squared minus 5x. Okay, once again, let's do another example where we get slightly more complicated again. This time our function is f of x equals the square root of x plus 1. So keep in mind that plus 1 is not inside the square root. So if we're going to find the derivative, we've got to use the limit as h approaches 0, and I'm going to plug in x plus h for x. And then I'm subtracting my original function from that. And all of it gets divided by h. Okay, so let me simplify this down a little bit first, because I can see already I'm going to have a plus 1 and a minus 1 when I distribute out my negative. So that'll make things slightly nicer. So at this point, it looks like we're doing a limit where we have some radicals involved. And if you think back to last chapter when we did limits with radicals, this is the part where we would multiply the top and the bottom by the conjugate. So we're going to do the same thing here. So the conjugate is going to be the square root of x plus h plus square root of x. And then we got to do the same thing to the top and the bottom, remember, because we're trying to not change the value of the original function. We're just going to be multiplying. It's kind of like multiplying by 1. So from here, when I multiply out the top, I end up with x plus h, regular without the square root, minus regular x, all over, and that h that was originally there with the square root of x plus h plus square root of x. So from here, the top can simplify even more because I can subtract x from the x plus h, leaving me with just h, which again, kind of nice, because then we can cancel that out with the bottom. So now I'm left with a 1 on top, and then this square root of x plus h plus the square root of x. Remember, our goal is just to make it so that we don't end up with 0 on the bottom when I plug in 0 for h. So at this point, if I plugged in 0 for h, I have x's left on the bottom instead of having like h times whatever, so 0 times whatever would still be 0. Which ends up being simplified to 1 over 2 square root of x. And since, again, for this year, I don't really care about rationalizing the denominator. If we have square roots on the bottom, so be it. Then this is our derivative. That's it. Okay, last example. So this time I'm looking for the slope of the tangent line for f of x equals 1 over x at x equals 3. So if they're asking us for the slope, really they're just asking us to find the derivative for the function 1 over x. And then at the end, because they're telling us x equals 3, we just know after I find the derivative, then I'm going to plug in x equals 3 to find the overall slope. So I started out by plugging in f of x plus h minus f of x into my limit. So from here, oh my goodness, I already have fractions on top of fractions. So think back to last chapter where we had complex fractions. We would multiply the top and the bottom by the common denominator. So in this case, the common denominator would be x times x plus h. And we're going to do this to both the top and the bottom. So on top, the x plus h's will cancel out of the first fraction, leaving us with just x. And then for the second fraction, the x's will cancel out, leaving us with the x plus h. But keep in mind, because I have that minus sign in front, it matters that the x plus h is in parentheses so that I remember to distribute my negative. And on the bottom, we have the h, we have the x, we have the x plus h. Okay, let's simplify this. So on top, we can definitely simplify because we're going to have x minus h when I distribute out that negative. And then, yay, things will cancel. Love it. And that leaves us with a negative h on top, which is nice because that h will cancel out on the bottom, which leaves us now with a negative 1 on top with the x plus h. But here I'm just going to start plugging in my h equals 0. So my derivative is going to end up being negative 1 over x squared. Okay, so that's my derivative, but I'm not done yet because they told us x equals 3. So now I'm just going to plug in x equals 3 to get negative 1 over 9. So when they ask me for the slope at x equals 3, it's going to be negative 1/9. So as you can see, all the skills that we've learned with limits in the last chapter are going to be applied here once we start with our derivatives here. So that's it for our derivatives section 1, part 1. We'll do some more kind of more difficult problems as we continue on with this section in the next video. Thanks for watching. Bye.